All right, let's look again at rational functions. We're going to put it all together in this lesson. So in summary, we have vertical asymptotes. Those go up and down. Their x equals some number. They're where the denominator equals 0 and did not cancel. There's a hole at x equals whatever number if the factors cancel. So vertical asymptotes are looking at the denominator. And an important note is that you can have more than one. So okay to have more than one. And your function will not cross. A vertical asymptote. Horizontal asymptotes and slant asymptotes come from comparing the degree of the top and the degree of the bottom. So both of these come from the same thing. Compare degree of p of x, which we call the top, and the degree of q of x, which we call the denominator. Compare them. You can only have one or the other. You can't have both. In some cases, you can have two different horizontal asymptotes, but that's unusual. So you can have vertical asymptotes with either one of these. You can have multiple vertical asymptotes, but you're either going to have the same degree, which would be the ratio of the coefficients, or you're going to have the bottom degree bigger. So bottom degree larger is going to be y equals 0. Or you're going to have the degree larger on top. And in precalculus, we stick to just solving when the degree is +1. You could actually do all of them because you know what end behavior looks like. You could divide it out and have the idea of a parabola or some other figure. So that might be fun just to graph for fun. But we stick with these in precalculus. And it's all about looking at the degree. For horizontal or slant asymptotes, we're looking at what are not allowed in the domain for vertical asymptotes. So let's look at some actual examples, put it all together, and see if we can sketch some graphs. If you didn't catch all that summary, please go back, rewind it, and pause the video and make sure that you have a summary of these different asymptotes. It's super easy to get them confused until you're really familiar, so I suggest you write it down as often as possible. Looking at example 1 and trying to make a graph, let's see what we can figure out. First of all, we need to simplify and see if anything cancels. So if I write this as x minus 1 times x, right away the denominator cancels, and so that means that a positive 1 at x equals 1, there's a hole. What does the graph look like? It looks like what's left. It's going to look like a line. In fact, it's going to look like y equals x, but at 1, instead of being 1, it's going to be a hole. So that's as straightforward as it gets. It, once simplified, does not have a denominator anymore, so it does not have a horizontal asymptote. It doesn't have anything to compare the degrees of. Example 2, x squared plus 1 over x squared plus 2x minus 15. So, looking at vertical asymptotes first, I'm going to factor this, x minus 3x plus 5. That gives me negative 15 and positive 2. The top doesn't factor. So, what do I have? I have vertical asymptotes at x equals, since nothing cancels, x equals positive 3 and x equals negative 5. And then I'm going to think about horizontal or slant. So now I'm looking at the top degree versus the bottom degree. They have the same degree. So this is going to be a horizontal, not a slant. And it's going to be y equals. And I compare this together right here. They're going to grow at the same rate. And they both have a leading coefficient of 1. So this is going to be y equals 1. So here starts my sketch. One, two, three, four, 5. 1, 2, 3, 4, 5. Okay, so I have some dotted lines to draw. My vertical asymptote at x equals 3 will be here. It's a boundary. I've got one at -5, so here. Different colors could be your friend here, so you can tell what's going on. Okay, I also have a horizontal asymptote at y equals 1, so it crosses the y-axis at 1, and here we go. Okay, keep in mind this is a function, meaning that I cannot graph in this space and this space, because then it wouldn't be a function, it wouldn't pass the vertical line test. So those little things that we've learned in our history of math will come to play a part in how we figure out how to graph this. Okay, let's also see if we can find any intercepts. So does this ever equal 0? If we take this and set it equal to 0, equals 0, what do we solve? So we're looking at a ratio. In order for a fraction to be 0, we can't have 0 in the denominator. It has to be 0 in the numerator. So we want to try to solve x equals, I'm sorry, not x equals. We want to try to solve the top. X squared plus 1 equals 0. Turns out that doesn't have any real solutions. So we do not have, there are no x-intercepts. It will never cross the x-axis. So that tells me several things. First of all, it tells me that I cannot have any graphs right here or right here, because in order for me to get from my graph is going to try to hug this dotted line, hug it, hug it, hug it, and then hug the top dotted line at some point, whether it's here, whether it's down here. In order for me to graph a function in this sort of category, it would have to pass this line to be able to hug this dotted line. So I know right now that without even plotting any points, my graph is going to follow this asymptote that's vertical and this asymptote that's horizontal and be up there. The same thing goes over here, and it's going to hug this asymptote and the horizontal asymptote like so. Now, I can do one more thing to figure out where it's going to touch the y-axis by plugging in 0 for x. So the y-intercept is always 0 for x and a value. Let's actually plug that in and see what happens. So if I take 0 here, I'm going to have 0 plus 1 over 0 plus 0 minus 15. 0 plus 0 minus 15 equals 1 over negative 15. That's my value right there. So what does that mean? It means that at 0 down 1/15, which is really close to 0, I have a y-intercept, which tells me that this piece is here, but it never crosses the x-axis, so it must sort of go like this. And I'm saying sort of because I don't know exactly what it looks like, but I do know that as it goes this way, it cannot cross the x equals -5 line. It has to come towards it and then try to follow the line. It becomes a fence. It's like those little fences, the dogs with the invisible collars, you know, they make a path in the grass because they can't pass the fence. They just have to go near it. And then this doesn't go above any of this axis. It doesn't approach right here, but that's okay. This dotted line is for end behavior. Remember, the y equals line is all about end behavior. So it doesn't necessarily predict middle behavior, just end behavior. So my graph looks like this. This is a decent sketch. You can see in the book they have the same sketch, and it looks about like ours. So how about that? Example 2, making a graph that's a little bit more interesting. Let's see one more. Okay, example 3 looks like a rational function. It has a polynomial of degree 2 on the top and of degree 1 on the bottom. This does not factor. Therefore, I cannot cancel this out and make it a whole. So what that tells me is that I have a vertical asymptote at x equals -1, strictly from the denominator. Then I'm going to compare the degrees, and I find that I have a degree higher on the top. So I've got a slant asymptote, and I don't know what that is yet. I'm going to divide it out and find out. So I'm going to say x plus 1 into -3x squared plus x plus 1. X and a -3x squared, -3x, -3x squared minus 3x. Change the signs. Cancel. 4x plus 1. X and a 4x goes 4 times. X. I'm sorry, 4 times x is 4x plus 4. And I've got, change the signs, -3 plus -3 over x plus 1. So I don't know how to graph lines that have this random piece at the end, and that's fine because this goes to 0 as we go to infinity, and this slant asymptote, which is y equals x plus 1, goes to infinity. That's what I'm looking at, so I don't care about this at all. I can drop it. These are the two features I'm going to start with in my graph. Okay, so I've got a vertical asymptote at x equals -1. I've got a slant at x, oops, I lost, why did I say x plus 1? I think I've lost my mind. I took it from my denominator. Okay, this is my slant asymptote, -3x plus 4. So 1, 2, 3, 4, and then down 3 over 1. So this is the slant asymptote here. So I could have drawn that in a better place probably. So here's the question. Is my graph going to be right here? Is it going to be in this quadrant right here? Is it going to be over here? I'm not sure. I'm going to need to plot some points. I would like to start with the y-intercept because that's so easy to figure out. That's going to be y equals 0 plus 0 plus 1 over 1. Excuse me. So it's going to cross at 1, 1 here. That means that my line is going to go, it can, it's going to follow this and then this way, because it has to follow the slant asymptote with the negative behavior. I'm sorry if this kind of goes off to the side a little bit. That's not very pretty. But anyway, I don't know my x-intercepts, but they're going to be about here. And it's going to have to cross twice there. That means that the other piece of my graph cannot be right. So this is process of elimination using logic. I cannot graph right here because then it wouldn't pass the vertical line test. Can you see it? If I were to graph it there, that would not work. I could graph right here, but look, I've already used up, this has 2 intercepts, and I don't know exactly what they are. I made this so it didn't factor, which was not smart on my part, but they're going to be numbers that have radicals in them somewhere here because I had to get to this point, 1, 1. And if I were to graph over here, that would mean I have a third x-intercept right here where it equals 0, and I can't. From the fundamental theorem of algebra, there's only 2, and they're here. That means that the other part of this graph is up here, and I don't know exactly what it does, but I know it's not, that wouldn't pass the vertical line test. It's going to come towards this asymptote and try to be the asymptote on this side. So there's that graph. I don't know why my light's so strange, but hopefully it'll fix itself. There you go. So it could not be over here because this would cross the x-axis as it followed this line down. It has to be here. And if you put in numbers into your calculator like negative 1.5, it's going to be a really large number. And it's going to turn out to be positive because this is negative over a negative number will be a positive number. So you could check it with a sign chart that way and see what it looks like. So what do you need to do to graph? You need to find your vertical asymptotes, the slant or horizontal asymptotes. You need to find the y-intercept. So this was the point 0, 1. And if you can, you need to find the x-intercepts. And then it's a matter of practice. It's fun to do your best and then put it in the calculator and see what you come up with. But keep in mind things like the vertical line test. These are all functions, so they have to pass the vertical line test. And also the fundamental theorem of algebra came into consideration here because I couldn't cross the x-axis again. So you have homework where you're checking all of these different kind of asymptotes, and then you also have where you're looking for inequalities. So that's one more thing we want to look at really quickly is inequalities. They're not a huge focus here, but we do want to touch on them as we're in this section. Okay, so now we're going to find intervals that satisfy a rational inequality. So here's a rational expression. It says greater than 0. We're looking for the values of x that when we put them in here, we're going to get a number that's greater than 0. So we're going to use a sign test for this. And first, we have to find out where we have any zeros or where we have any values that break the domain and make 0 in the denominator. So we're looking for zeros in the top and the bottom. So we're going to say x squared plus 1 equals 0 and try to find any for the top. This does not have any. Positive number plus a positive number cannot equal 0, so the numerator has no values. The bottom one, if we factor it into x minus 3 and x plus 5, and set it equal to 0, we would get the values x equals positive 3 and negative 5. So let's put those in a number line. And let's put negative 5 in the small part, 3 in the big part. And what that does is it breaks up our domain into intervals. The first is negative infinity to negative 5. And again, we're looking at it not equal to 0, so we're going to put a soft bracket for negative 5. I'm waiting for the light to clear. Okay, so not including 0. And then this middle interval, which is negative 5 to positive 3. And then the interval from 3 to infinity, all soft brackets because it's not equal to 0. And now our sign test, we're going to plug in numbers and see what kind of values we get. So we're going to test values and find out if it's positive or negative by plugging them in. So here's what I'm going to plug in. I'm going to plug in x squared plus 1 and x squared plus 2x minus 15. And we're going to pick a value in this interval and test it. Let's pick negative 6. I'm just going to put that in a little circle because that's going to be my test value. I'm going to plug in negative 6 and square and add 1. That's a positive number. Negative 6 squared is 36. Minus 12 minus 15. That's 36 minus 27. That is also a positive number. So that means if I say a positive number divided by a positive number, I'm going to get a positive number. So this is a positive number. It's greater than 0. So this interval is good. This satisfies greater than 0. Let's test a value here, like 0. It's the easiest one. 0 plus 1 is positive. 0 plus 0 minus 15 is negative. This interval, no matter what number you plug in, is going to be negative. This does not satisfy because negative numbers are not greater than 0. And plugging in here, if we plug in something obvious like 4, we're going to get a positive number, and we're also going to get a positive number. Divided together, they make a positive number, and so these two intervals satisfy this equation. So we're going to say that the solution where, let's just call this f of x. Let's say f of x is greater than 0 on negative infinity to negative 5 union 3 to infinity. So the sign chart, really helpful here. Gets us a little bit more practice with the sign chart. You want to find your zeros, put your zeros on the sign chart. These are the zeros in black. Test values around them. You're just checking for the sign, positive or negative, and whether that makes sense with this or not. So what you want to do if you don't have it set up like this is you need to move any expressions over to the left side and make it greater than or equal to 0 so that you can put the zeros here. So set it equal to, not really equal to, but make the inequality have 0 on one side so that you can use the sign test for these problems. All right, and that's the end of this 4.5 section. Thank you.